Hello. In this video, let us discuss one example for RSA algorithm. Let us recall the RSA algorithm that we discussed in the previous session. We are selecting two large prime numbers at random. So they are P and Q. And then we are going to compute n such that n equal to P into Q. And then we are going to find pi of n is equal to P minus 1 into Q minus 1. And selection of a random number E such that it is co-prime with pi of n and this is less than pi of n, and finding the decrypting key D such that D is the multiplicative inverse of E in modulo pi of n domain, and publish the public key as E comma n and keep the secret key private as D comma n and apply the encryption and decryption using these formulas. Now let us examine how it is working for one example. We are all having the steps here for our reference. So now, for example, I am taking that P equal to 3 and Q equal to 11. You may wonder that my first step is taking two large prime numbers, why we are taking small numbers. Actually, for practicality and for security, we are supposed to take large prime numbers, but for human calculation, for understanding, we are taking small numbers. Now, P equal to Q 3 and Q equal to 11. And next step is computation of n equal to P into Q, so which is given by 3 into 11, which is equal to 33. The next step, pi of n, which is equal to P minus 1 into Q minus 1. So 3 minus 1 into 11 minus 1, which can be given as 2 into 20, which is, 2 into 10, which is 20. Now, you are going to choose the next step, select at random any key as E, which is such that E should be co-prime with pi of n. Here, pi of n is 20. Let us take here E equal to 7. So let us, I am taking E equal to 7. So now prove GCD of, find GCD of 20, 7. So I can write 20 can be written as 7 into 2 plus 6. So then I can bring here 7 here can be written as 6 into 1 plus 1. Then again 6 can be written as 1 into 6 plus 0. So when I write 6 equal to 1 into 6 plus 1, when I have the remainder equal to 0, when I have remainder equal to 0, then this divisor will become the GCD. So I am getting GCD of 20, 7 equal to 1. So we use the Euclid's algorithm and check that GCD is equal to 1. So that means both 7 and 20 are co-prime. So I choose an E. Now I'm going to calculate D. So D should be E inverse in mod pi of n. So which is equal to 7 inverse mod 20. So we have to find 7 inverse mod 20. So we can use, it is easy to find that 7 into 1 equal to 7, 7 into 2 equal to 14. They are all less than 20. When you take 7 into 3, it is 21. 21 mod 7 equal to 1. So this means that 3 is the inverse of 7. So this means that I can have 3. So D equal to 3. So now I can make my key pairs. So the public key pairs E comma N equals 7 comma 33 and your private key or D comma N, which is equal to 3 comma 33. Now we have the key pairs. Now for this, let us take one example in m equal to 2. For my message m equal to 2, let us try to find this hypertext C equal to m power e mod n. We already discussed that in our example that MC equal to M power E mod N. So I want to find the code word. So C can be given as 2, M equal to 2, E equal to 7 mod 33. So we can use the model exponents to calculate. We already discussed how to calculate 2 power 7 mod 33. We know that expand 7 in binary we get 111. So power 1, 2, 4. So I can write 2 power 4 into 2 power 2 into 2 power 1 mod 33. So for knowing this model exponentiation, you can watch my previous videos. So first let us find 2 mod 33 is equal to 2. 2 square mod 33 is equal to 4. Mod 33 which is equal to 4. Next 2 power 4 mod 33 equals 2 power 4 is 16. So 16 mod 33 is equal to 16. We can continue 2 power 7 mod 33 equals 2 power 4 into 2 power 2 into 2 power 1 mod 33. So which can be given as 2 power 4 is 16 into 2 power 2 is 4 into 2 power 1 is 2 mod 33. So which can be given as 16 into 4, 64, 64 into 2, 128. 128 mod 33. 128 mod 33, we are getting 29. So we are getting 2 power 7 mod 33 equals 29. So this is the code word for the message M equal to 2. You can also directly write 2 power 7 equal to 128. But it is better to use the modular exponentiation method. Now let us see how to decrypt the same and find whether we are getting the C. We know that M equal to C power D mod N. So we got C is 29. Power D we got is 3. 29 power 3 mod 33. So this is equal to, can write 29 mod 33 to power 1 into, so 29 power 1 into 29 square mod 33. So 29 mod 33 is 29. 29 square, let us discuss 29 square mod 33 equals 29 square is 841 mod 33, which is equal to 16. So when you take 29 power 3 mod 33, which is equal to 29 into 16. This is for 29 power 1, this is for 29 power 2 into mod 33. So which gives 464 mod 33. When you take 464 mod 33, we get the remainder is 2. So we got back the message M. So this is how we encrypt using the key public key of 7, comma 33, and we decrypt using private key 3, comma 33. We are able to get back the original message. This is how RSA algorithm works.